So we are interested with the propagation of an incident acoustic field that take into account rigid body diffractions. So for this kind of problem, we have several methods. So we have the boundary element method. So this is a complete method, but it's quite complex and time consuming. It requires some fine mesh management expertise and can have some non-Nucleus issue. On the other side, we have this equivalent source method developed by Kuhlmann, which is based on the superposition principle of a fundamental solution of the Helmholtz problem. So here we put some elementary source inside the body, and we put this source to be to have the boundary condition and used by the incident field. And then we can repropagate outside the body, the acoustic field, and this can be considered as the equivalent as the presence of the rigid body. So this avoids numerical singularity that we can have in BIM. So this ECM is used to find some acoustic pressure on 3D radiating bodies. So this is a company in Lyon that asked us to work with them about this technology of ECM. So we work on the solutions of the linear systems that are involved in this methodology. So we have, so there are some microphone, array of microphone, so M array of microphone. So they want to put some equivalent monopolar source in the rigid body, given at a pulsation frequency omega. And they pressure, they look at the pressure they have, and then they retropropagate the equivalent source to obtain the pressure at the surface of the skin. So they do here. So here we are interested in the calibration step. So it's to find the equivalent source, such that for a source outside of the body, we want to have the same source normal velocity between this source here and the equivalent source here at the boundary of the skin here. So we have this equivalent source to normal velocity transfer matrix. So TSG here, we have this form which depends on the angle between the equivalent source and the body. On the node on the skin of the body, and we have the same for the transfer from the source to the velocity at the body. So we want to have to solve this linear system here, and there is some difficulty to solve this system because we have a non-determined system because we have more nodes on the skin than the number of equivalent source. It's dense, so each equivalent source affect all the node on the skin, and it's ill conditioning. So we have something like this form here. And so the form, I recall here, the form of the matrix coefficients. So what we want to do is to use domain decomposition method to solve this linear problem with the hope to reduce the size on the ill conditioning. So the idea is to take the initial problem, then to split it in subdomain, and then try to solve by a Schwartz method iteratively to obtain the solutions with having some reduced representations of the other subdomain in the algorithm. Historically, domain decomposition appear to reduce the conditioning of definite positive systems. So we want to have the same idea. But here here we have a difficulty because we have two sets. Sorry, I think we have two sets of point. We have the set of the n boundary points, and we have also the set of any equivalent source. So we have to decompose a domain that take into account these two sets of points. So we define a pair. So a subdomain is a pair of a part of omega L, and a part of big omega L. So this subdomain can overlap or not. And then we apply the additive Schwarz. So for the point on the boundary, for the subdomain omega L, we have to iterate for the domain of the source, equivalent source here. We take here it implicitly, and we put the other part of the other contribution explicitly on the right-hand side. And then we iterate from n, and we take the previous solution to compute the next solution, etc. So the property of the Schwarz method, if you have a well-posed linear system, is that its convergence or divergence is purely linearly. So we can have an error operator, and such that we can write the error between two successive iterates like this. And if one is not in the eigenvalue of this operator, then we can accelerate it to the solution by the Eichen accelerations. So we apply this a lot of time, and we succeed to solve large-scale ill-conditioned system for Darcy flow, for example. So the idea was to try to have the same methodology for such problem, for the SM problem. But the difficulties encountered here to adapt the DDM. First, the matrix is not square, and it's complex, but this is not a problem that is complex, but it's no square. That is a problem. And the third thing is it is in the least square sense. So what will be the effect on the domain decomposition method, convergence? And also, R is a dense matrix. So each source contributes to each control point. So we don't have a natural interface that we have naturally in a partial differential equation. So how to split the domain? Because we don't have a limited data dependency, but all points affect the result. So from the mesh on the surface, so the control point, on the source equivalent size object, first we divide the surface in n partition using METIS, graph partitioning, and based on the adjacency of the vertices. And then we assign to each equivalent source the rank of the nearest control point using a KD3. So, for example, for this one, we obtain they are associated to this point. This point are associated to this control point here. So that's what I say. So we use a Schwarz. So as I say, we have to solve this linear system. And here we have to solve for the block diagonal here, the pseudo-inverse, because we don't have square matrix. And here you have in blue, the difference between two iterate, the local solve here for the max of the local solve for each subdomain, for all the subdomain, and here the global residual. So we see that with this geometrical splitting, we don't have a convergent method. We try to make some relaxations with taking only a part of the new solutions. So this gives some convergence, but we see that after some moment, after a moment, the method starts to diverge. Even with a very small relaxation parameter, we see that here we have some instability in the algorithm that it starts to diverge here. So with looking more, we see that if you here we have computed the singular value decomposition of each block, and we keep here the percentage of singular value above 10⁻12. And we see that for this control point here, we see that some equivalent source here still have some influence. And this influence is not taken into account in the implicit solving of the Schwartz iteration. So it's why we have this kind of some divergence after some convergence here. So what we think is that we need a numeral criterion splitting. So the idea was to take into account the factor 1 over R is the matrix coefficients to gather neighboring block of unknowns. So we split the matrix R in M by M blocks. So here 3. And we compute the singular value decomposition of each block. And then we define a threshold criterion of the percentage of number of singular values greater than a threshold epsilon. Then we define an indice L, which has the max of the singular value which are greater than epsilon. And this defines a percentage tau, e.g., for each block. And then we define an adjacency matrix, B, where the coefficient of the matrix is 1 only if the criterion is greater than the threshold we have fixed. So this gives us this kind. So we start with a lot of subdomains. We compute the threshold, the criterion, the numerical criterion. This gives us this matrix here, adjacency matrix. Then we make a Cutting-McNee reverse algorithm to concentrate the profile. And then we gather blocks that are close together. So they give us now our new domain decompositions with the numeral criterion. And here it's approximations when we recompute with this here, the difference between the two, between the approximation we made here and the original matrix. Yeah. So then we can define a project Schwartz algorithm. So here what we do, we take in account now it's a 1D splitting here. So we take the column here, we define this matrix, and we pass this unitary matrix here in the other side. For each block, for each iterate, for each row for x1, x2, x3, we have to solve this equation here, where we put this unitary matrix here in the other side. Okay. So we can rewrite this like this. So for each component E, we have a matrix A bar E. We have project the residual where we don't have the E component. So this gives us this step for the Schwartz for each component E of the subdomain. And this comprises the local system. So these problems are solved by SVD decompositions. And we have a better conditioning than the full system. So the first full system, the conditioning was 10 for 8, nearby 19. And here, each subsystem, it's about between 8 to 9. So it can become more reasonable for this. So here, it's to show the compressing. So we saw that for the log diagonal, so this is the column here. We have nearly the same. You sum all these terms here. You have, you should have, if I remember well, 3,2000. And here it's the compression we obtain. So the other columns here are compressed. So the non-compressed column is this size. And for the first component, the 408 here was compressed by to be 323, for example. Okay, so we have this compression of each system. It's about between 34 to 40 with this 3-hole with tau to be 0.8. And this for the SVD complexity. So the SVD complexity is in big tau of n, ns on the minimum of n on ns for the matrix A. So we have a numerical speedup for the SVD compressing due to the methodology to be m over this key, this compression factor here. And if we do that in parallel, it's m squared over t. So now we saw the Schwarz convergence. So we see that now we're starting from the initial guess 0. We begin with a rapid convergence, and we have after a slow convergence. So we see that it's about 10 iterations here to achieve here. But we see that we need some acceleration to be competitive. But even we're starting with the initial guess to be with computing with the SVD of A, the initial guess here. And then we start the Schwarz. We see we still improve the solutions with the Schwarz methodology compared to what we did before with the SVD decomposition of the full matrix A. So here we increase the size. So we see that we increase the omega frequency. So this increasing of omega frequency give a better Schwarz convergence. We see that it's better straight line here. But we need to adapt the tau compression parameter. So we had to put here 0.9. And we still have a good compression of a subsystem. It's between 26 to 33%. And if we increase the number of subdomains here, so the increasing of the number of subdomains, so this increases the key subsystem compression, percentage compression. So it's about 28 to 37% compared to 26 to 33% for a subdomain here. But that doesn't degrade the Schwarz convergence behavior. So we still have straight line with few iterations. But this degrades the final residual. So we have only here about 10 minus 5 compared to 10 minus 7 with a subdomain. So here it's what we see the decomposition of the singular value for each block that have been gathered. So conclusion and perspective. So we succeed to make a convergent Schwarz. So this is the projected Schwarz. This improves the conditioning. This compares the local systems. And this have a better Schwarz conversion behavior for high omega frequency. So we need to still work on the icon acceleration because it's really need to have a very competitive method. And another things we think things we think it's work on the initial guess. So start from a square system. So select some equivalent source. So here we are in the theory of the Schwartz with a square matrix. So we can apply the Einstein accelerations and obtain an initial guess, and then apply this initial guess to the other solution, And then also to write on the we working on the parallel implementation with using CFC, and it's not finished. So thanks.